Hi Surinder, we'll start shortly in a few minutes. Thanks for joining. Hi Surinder, are you able to see my screen?
Yes, it is visible, sir.
Okay, yeah, so let's start. So now we'll be discussing some sample problems for week 5 of the course Metabolic Engineering. Um, yeah, so the first question is the below represented reaction network consists of three metabolites, three internal reactions, and three exchange reactions. How many elementary modes are present in this network? Let's take a few minutes and then we'll discuss what or how many elementary modes are there in this given network.
Uh, shall we discuss that question?
Yeah, sure.
Mm.
Yeah.
Actually, I am not getting the answer, correct answer.
Okay, sure. I'll tell
Uh-huh.
what we have to do. So, elementary modes are nothing but ways in which you can connect internal fluxes with external fluxes. It is simply that what you see here is a reaction network with three metabolites. I hope my pointer is visible. The metabolites here are
Yeah.
A, B, and C. A can both enter and exit, whereas B can only enter and C can only exit.
Mhm.
Now,
Mm.
what we have to do is we have to find ways in which a metabolite enters and gets transformed and then it exits, or vice versa. That is what we do
Mhm.
with elementary mode analysis. So, if you consider that, since A can both enter and exit, one of the elementary modes will be in which A will enter, it will get transformed into C, and then C will exit.
Mhm.
The other elementary mode will be B will enter, get transformed into
Mhm.
A, and it will exit. Now we've
Mhm.
covered both the entry and exit of A.
Okay,
Now we
okay.
have to see other metabolites. For example, in this case, B doesn't just get converted into A, it can also get converted into C. So the third elementary mode will be B entering, then it's getting converted into C and it's exiting. And apart from this, there is an internal reaction where B can enter, it can get converted into A, and A can get converted into C, and it can exit. So these are the minimal possible paths through which you can connect uh, metabolites entering and exiting, flux entering and
Yeah.
exiting out of the system. These are called the
Mhm.
elementary modes.
Okay, okay.
So this is how you calculate the elementary modes. So the
Mm.
right answer is
Four.
option B,
Four.
4. Yeah,
Okay, okay.
yeah. If you have any further doubts, we can
No, no.
discuss that for this
Clear, clear,
question.
clear.
It was clear. Okay, okay. In the next question is, what does negative value of reduced cost implies? And the options given here are increasing the flux Vj would reduce the objective function value. Option B, increasing flux Vj would increase the objective function value. Option C, decreasing flux Vj would reduce the objective function value. Option D, all of the above. We'll take a few minutes and then we'll discuss how to approach this question.
So I think it is C. Decreasing flux would reduce the objective function value.
Okay. Uh, okay, you can try to like share what you understand from this, and then we'll discuss why that is right or wrong. So we can start with what reduced cost means, and we can take it from there. So you can share your understanding. Yeah, please. So mathematically, like, would you want to talk about what reduced cost is?
Mhm.
Yeah, you can then tell us. Yeah.
So objective function, if we reduce the flux, then automatically less carbon will flow. So that's why I am thinking it is reduced cost.
Okay, so reduced cost is a metric. So how these reduced cost has been defined is that it is the amount by which the objective function will be reduced if a particular enzyme is forced to carry a flux, which was initially not carrying a flux before. So how you can understand this is in a given metabolic network at a particular time during steady state, not all the enzymes carry a particular flux. Okay,
Okay,
but let us say we are having an enzyme and we are asking or we are forcing flux to go through that enzyme.
okay.
Now, because flux is going through the enzyme, this there is a reduction in the flux that initially went through other enzymes. And because this flux is going through this particular enzyme, it would lead to new products and a new set of reactions. So,
Mhm.
what we calculate here is how the objective function or how much the objective function will decrease if we force a particular enzyme to carry a flux. That is the way in which reduced cost has been defined. So mathematically, how it is defined is you have to the objective function is is given as a equation. You have to now determine the flux for that particular enzyme. So let's say there are two variables. One variable is the objective, one equation is the objective function in which you have multiple different variables, which is flux of all the reactions that are active and the corresponding weights. Is this clear?
Mhm.
Now,
So,
if you
mhm,
differentiate this objective function with respect to flux of the reaction you want to carry for, like there is an enzyme, you want the enzyme to carry a flux. Now, if you differentiate the objective function with respect to this and give it a negative sign, this is called as the reduced cost. Yeah, you had a doubt, is it?
so if more flux is going through a forced enzyme, then it will be negative.
Yeah.
If more
So
flux is going through a forced
forced
reaction.
enzyme. Yeah, you're right. So
Mhm.
the right answer is, like as you said, increasing that flux would reduce the objective function. It is like biologically what we can say is we have an enzyme that is not usually active, but we are forcing our system such that it is becoming active. Now, how will the biomass change? Will it increase or decrease? And because this enzyme is not necessary, if you are forcing it to have a flux, then of course the biomass would reduce. So the answer for this question is option A. Increasing flux would reduce the objective function value.
So increasing flux, it is not saying na through which enzyme,
No,
normal
no.
enzyme or forced enzyme.
So reduced cost can be calculated for all the reactions.
Okay.
So in general, reduced cost has been defined such that we don't have that enzyme carrying a flux at steady state in general. But reduced cost can be defined for all the fluxes, all enzymes. And in this case, we are taking the literal definition of reduced cost. So we are seeing how the objective value would change when a new enzyme is introduced or an enzyme that does not contribute to the biomass is introduced. Because it doesn't contribute to biomass, when flux is being forced to carry through that particular reaction, biomass would reduce. Was it clear?
Ah, yeah, yeah, yeah.
Okay, okay. So even in the solution, they say that reduced cost RC shows increasing flux would reduce the objective function value. If it's not biologically clear, I'll explain that again.
Clear, clear.
Okay, okay. Huh. So the next question is null space of a stoichiometric matrix contains A. All the steady state flux solutions to the flux balance equations. B. The dynamic flux vectors. C. The time derivatives of metabolite concentrations. D. None of the above. We'll take a few minutes and then we'll answer this question.
So in this, actually, I have one query also.
Yeah, yeah, sure.
Yeah, how to calculate the null space?
Null space is nothing but equating it to zero. That is the null space.
Hmm.
So you have two different matrices. One is your stoichiometric matrix or the S matrix that gives you information about how what metabolite participates in what reaction in how many stoichiometric units. That is what your stoichiometric matrix defines,
Mhm.
right? And the
Mhm.
other matrix is actually a vector, which gives you an information about what are all the possible fluxes within that. Basically, the kind of reactions, all the reactions. So it will be along the dimensions of m cross n into n cross 1. Now, because this is at steady state, meaning whatever enters the cell, it either gets converted to another product or a series of products and then exits, or it exits the cell. Basically, there is no accumulation. This is what we call as the steady state. Now, at this particular condition, because there is no accumulation, on the right hand side, you can equate the product of this stoichiometric matrix and the vector equal to 0. This is the null space. Was that clear?
Ah, yeah, yeah.
Okay. Huh.
So,
So, yeah,
it's steady state flux solution.
yeah, that's the answer. So, what we get from the null space, the stoichiometric matrix, is that at steady state, what is the flux value for each of the different fluxes
Mhm.
that can possibly enter the system, enter or exit the system? Yeah. So, the right answer is option A. All the steady state flux solutions to the flux balance equations. This is what is contained in the null space of the stoichiometric matrix. Yeah. Uh, the next question is classify the type of extreme pathway from the below represented reaction map. So here what you have is in green is the system of your interest. In yellow is the region where metabolites that can be exchanged within the system is present. And what you observe here is a cyclic loop where metabolites within your system are just getting interconverted into each other, and nothing from the exchange metabolite either enters or exits your system. So the cofactor pool remains unused. Now, what they're asking is we have to classify what kind of extreme pathway is shown in the map here. And the options they give are type 1, which is primary metabolic pathway, type 2, which is futile cycle, type C, type 3, which is internal loop, and a fourth option is none of the above. So we can take a few minutes and then we can answer this question.
It's a futile cycle.
Futile cycle. Do you want to first go through what each of these different types are, which is like type 1 primary metabolic pathway, type 2 futile cycle, type 3 internal loop, before which we finalize what the right answer is? Do you want to share what you think about this primary these different types?
So, primary metabolic pathway is, for example, glycolysis, where the conversion of glucose to pyruvate. So, the metabolic pathway, where pyruvate is converted to the two molecules of glucose. Sorry, glucose is converted to the two molecules of the pyruvate. So, it is the primary metabolic pathway.
Okay,
Okay,
okay.
and futile means if, for example, glycolysis and gluconesis they happen at the same time.
Hmm.
One side glucose is converted to pyruvate, other side pyruvate is again converted to the glucose.
Okay.
So nothing we are getting from that. Only the expenditure of the energy happening here.
Right.
So these are considered as a futile cycle.
True.
So in this diagram also, for example, if we start with A is convert to B
Okay.
convert to C
Okay.
convert to D, and D again convert to E.
Okay.
Okay, and cofactor pools is using. It is utilizing here.
In you're
So
talking about in futile cycle, are you saying that cofactor pool is being used or in primary metabolic pathway? mentioning? Which of the options are you talking about? Futile cycle, is it?
I'm talking about in cofactor pool. Obviously, it will use and it will be replenished also cofactors.
Hmm.
Okay, in both cycles.
Okay. Hmm.
Cofactor required in the primary metabolic pathway also as well as the futile cycle also.
Okay.
So, and internal loops, I have no idea about the internal loops.
Okay.
So that's why I chose this option B, futile cycle, because metabolize is recycled. Okay.
Okay. Okay. So, mm, how it has been classified for the types of extreme pathways is that in type 1, the primary metabolic pathway, like you've given an example, we have a substrate that can enter the system. Then it
Mm,
gets converted, then it gets exited. And
mm,
when when the substrate is getting converted into product and as it exits, this process requires cofactors. So from the cofactor pool, cofactors being utilized and it's being replenished. That is the type 1 primary metabolic
mm,
pathway, like you mentioned. Whereas in futile cycle, what happens is, like you mentioned again, cyclically, a substrate gets converted into product and product gets converted into substrate in a cyclic fashion.
mhm,
But apart from that, what has been mentioned is that from the cofactor pool, only the only few specific fluxes are active. Not
mhm,
all the fluxes from cofactor pool is active. Whatever is needed to sustain the cell, these are called the currency exchange metabolites like ATP. Only those are active. But in futile cycle also, this cofactor pool, it interacts or exchange of the cofactors from outside within the system occurs in futile cycle also. But the difference between futile cycle and internal loop lies here. In internal loops, there is no active exchange fluxes, meaning there is no connection linking the cofactor pool to the reactions within your system. These are called internal loops.
okay.
And what we
Means
see,
this green is happening independently.
so
They
the
are not
green,
required cofactors.
yeah, green is happening independently. Cofactors are not required for the process. 1 minute, someone has joined. Huh. Yeah. So the green process can happen independent of the cofactors, so no exchange is required. And what we observe here in the diagram is that in from cofactor pool, no entry or exit happens. So what is shown as an extreme pathway here is type 3, which is internal loop and not futile cycle. For futile cycle, it is called a futile cycle because some energy expenditure is happening from cofactor pool, which is wasted because it is cyclical and it is not getting replenished. That is why it's called a futile cycle. Whereas in internal loop, no such cofactor exchange happens. So it's just a loop. Ah, was that clear?
Mhm, yeah, yeah, yeah. So
Okay.
in internal loops,
Ha.
uh, means here we are talking about the cofactor. Can we say internal loop reaction they are happening independent of the ATP
Cofactors.
also? Oh, yeah, only cofactor.
Okay.
We have to stick with the cofactor.
So you need to consider this at the reaction level and not the cell level. So what you can say is you can't, okay, how to imagine this is you cannot claim or say that only when glucose is provided to the cell as a raw substrate, other reactions can happen. You cannot bring in the big picture, but rather you can consider a pathway which is cyclic and does not require cofactors or
Okay,
exchange of cofactors. That is the way in which
internal
this has
loops.
been, internal loops has been defined.
If some arrows are given in opposite directions, means from
Okay,
yellow to green and green to yellow, then it will be
okay.
futile.
It will be futile because what happens here is cofactors are being taken for
Mm,
this cycle, but the cycle does not produce or replenish the cofactors. So cofactors are in the energy currency, which are also can be termed as cofactors. It's actually being consumed and not being replenished, which is wasted, which is why it's called a futile cycle. Was that clear?
Yes. Clear, clear.
Okay. Uh, Kritika, we've started discussing. Once we are done discussing all the other questions, we'll go to the questions that you had missed earlier.
Okay, sir.
Yeah. Was this clear to you, or should I repeat the explanation for this?
Yes, sir. This one is clear, sir.
This one is clear. Okay. So what they mention is this is internal loops only. There is no active exchange fluxes in it, like we had discussed. Okay. So the next question is Upstream uses which of the following databases? Kyoto Encyclopedia of Genes and Genomes KEG. Option B is Metacyc. Option C is Database of Enzymes and Metabolic Pathways EMP. And option D is all of the above. Yeah, we can take a few minutes and then first discuss what Upstream is and then decide which of the options are right here.
So, shall I start?
Um, mm, we can give a chance to Kritika because she's
O-
just joined now, and then we can have a
hmm,
discussion. Yeah, Kritika, do
Okay.
you want to answer, or if not, Mr. Ranger would answer?
Sir, option A is correct. Like what I've studied in lectures, so
Hmm.
only KEGG is the database which is present in Opstrain.
Okay. Surender, what about you? Do you want to share your answer?
So it's obstain. It is a redesigning of the production system.
Right,
Okay, so for redesigning of the production system, we require the genomic information, we require the information of enzymes,
right,
every metabolic pathway. So, for mine opinion, answer should be D,
right,
all of them.
right. Yeah. So, yeah. So how we can understand this is like Surender had mentioned. Um, Obstrain is used to improvise a particular metabolite. I mean, a particular strain to produce a particular metabolite of our interest, which means we have to have an idea about what are all the genes are present, what are all the genes are involved in the reaction, which gets converted into the proteins or enzymes, depending on the pathway, and how this pathway can be branched into different metabolic pathways, which means that we need information about genes, genomes, and the enzymes and the metabolic pathways. So the right answer here is that Opstrain uses all the above. Uh, that is the necessity for Opstrain. So what Opstrain or how Opstrain functions is first reactions and genes from the databases is added. Then it would try to then we can specify what is the product or the substrate that we'll have that is of our interest, depending on which reprogramming would happen to give us a strain that is compatible, which requires all the information, which is why all the three databases, KEG, which is Kyoto Encyclopedia of Genes and Genomes, Metasite, and database of enzymes and metabolic pathways, EMP. All these three are utilized in the process. Uh, was it clear, Kritika?
So what does metapsych involve?
Metasync is also another database that I can even share my screen. Give me a minute. Okay, it's taking a lot of time to load, but what we can summarize is in MetaSite, you have information from different organisms combined for a particular reaction or a gene of interest. There could be redundancies from what you see in Metapsych and KIG because both of them store information about genes, genomes, and proteomes from all the organisms. Here, but it does cover information from KIG as far as I am aware. Okay, what has been mentioned as the difference between Metapsych and KIG is that despite it contains the same information, KIG has information for more compounds than Metapsych, whereas Metapsych contains information about more reactions and pathways than KIG. So it appears as if Metapsych and KIG can complement each other. That is what is mentioned as the difference here, Kritika.
Okay, sir.
Yeah. So yeah, I'll go back to the PPT. Yeah, you are able to see my screen, right? Yeah. So the right answer
Yes, sir.
is option D, which is it curates information from all databases, then identifies the reactions for product yield optimization, which is what we had discussed. Huh. Now we'll be talking about this question. Which of the following options is not true for the hit and run flux sampling algorithm? Option A, this is a Markov chain Monte Carlo sampler. Option B, it estimates the center of the solution space in a warm-up phase. This estimate is then continuously revised with further sampling. Option C, random direction in step choice to go to the next point. Option D, reduce the number of steps needed to converge to a uniform distribution. Yeah, we'll think about this and answer this question in a few minutes. Yeah, Kritika. But before you start answering this question, you can first share what you think about this flux sampling algorithms in general, and then talk about why you think a particular answer is right or wrong.
Sir, I don't have any idea about this exactly.
Uh, can you repeat again? It was not very clear to me. Hello?
Uh,
Yeah.
yes, sir. Like flux sampling algorithm. What actually I understand there is um like these are the basically methods to so like I can't frame sentence to explain this actually.
You can take your time. Like we have enough time. If it one, you can try answering. Even Surender can answer. If we have difficulties, then I'll try explaining. You can take your time and explain. We have enough time.
So like in lecture, what I've
Huh.
seen that there is a flux flow diagram.
Okay.
So like we have metabolites and then reactions arrows are represented by V1, V2, V3.
Right.
So we have to find those flux values.
Huh.
So we use these methods like this hit and run. We have another one that is artificial hit and run algorithm. So we basically use to get the flux values
Right.
of those representations.
Okay. So, do you understand what flux sampling algorithm is?
So, flux solution, flux sampling.
Yeah.
Uh, how flux is flowing in the cell?
Huh. That it basically gives you.
If, for
Uh.
example,
Yeah.
we are
Hmm.
giving the glucose, then how the glucose carbon is being metabolized means how the carbon is going. If you are giving another thing, another molecule, then how the flux is being changed. Okay, I think that is the flux sampling. Means uh, feasible fluxes.
Huh. So, like, yeah, both of you had have an understanding. I'll just add on to what you were mentioning. So, what we have in a metabolic network is a set of reactions with metabolites, and depending on a particular constraint, we try to, using mathematical optimization procedures, we try to assign fluxes for a particular reaction such that the constraints are fulfilled. Is that first clear with respect to flux balance analysis for both of you?
Yeah, yeah, yeah.
Yes, sir.
Yeah. So what happens is that we have a flux cone in which multiple different options or multiple different flux values are possible. They are feasible solutions, which
Mhm.
means that let's say there are two reactions and two unknowns. Like for example, x plus y or two reactions. or how do I say, in in a, we have, okay, with respect to metabolic engineering, we'll have a given set of reactions and metabolites, but we don't have constraints for all the reactions or the metabolites, which means that we will have many unknowns than the number of knowns. This means that mathematically, uh, more than one particular value can be given for one particular flux. There can be different combination of fluxes that can satisfy the same criteria that we are imposing. Is that understood?
Yes, sir.
So because we'll have many different combination of fluxes, we need to identify what is the right flux. That is a problem. That is why it's always suggested to have as many constraints from with respect to data from experiments or literature. As many constraints as possible so that we have minimal number of combination of right fluxes. So this flux sampling algorithm, what they do is, inside the flux code, they try to assess or go through each of the possible combinations and identify the right flux combination. This is what the flux sampling algorithm does. Is that clear?
Hmm. Yeah, yeah.
Okay, okay. So here they have asked for a specific case of flux sampling algorithm called as the hit and run flux sampling algorithm. So they're asking which of the following is not true. Generally, what happens is these algorithms are aimed to start at a random position, then iteratively improve such that they reach the right set of flux combinations. And this means that option C, which is random direction and step size choice to go to the next point, is right. And also, because this is iterative and wants to converge, the option D, reduce the number of steps needed to converge to uniform distribution, that is also right. Whereas this entire process itself, it has some random stochasticity to it, which is defined by the Markov chain Monte Carlo sampler. So option A is also right. So the what is not suitable for this hit and run flux sampling algorithm is that they say that it estimates the center of the solution space in a warm-up phase, then estimate is then continuously revised with further sampling. This is the wrong option among the four. What I can do is possibly when I add this video to YouTube, I can give a brief explanation as to how hit and run flux sampling algorithm works. So you can check that, and if there are any doubts, you can ask me further. Is that
Okay, sir.
fine? Okay, sure.
Yes, sir.
Okay, thanks. Yeah, so what they say is the hit and run flux sampling algorithm can't estimate the center of the solution space in a warm-up phase. Right. Huh. So the next question is uh, metabolites with a positive shadow price. What happens? Or what is the impact of metabolites with positive shadow price? The options are adding metabolites will decrease the objective function value. Adding metabolites will increase the objective function value. Option C, it doesn't affect the objective function. And option D, removing the metabolites will increase the objective function value. We, we can take a few minutes and then first discuss what shadow price is. Then we can decide how uh, positive shadow price or a negative shadow price will affect an objective function. You can take a few minutes. Yeah, Kritika, we'll just take 2 more minutes and then we'll try answering this question.
Okay, sir.
Yeah, Kritika, so you can first share what you understand about shadow price. We'll take it from there.
Yes, sir.
Yeah.
So basically, it's a basic definition that it's a derivative of objective function with respect to the exchange flux. So if there is any change in the exchange flux, it will, if there is any change in shadow price, this will affect the exchange flux, and then our objective function will also be affected with it. For example, like here, it is given that if metabolites with a positive shadow price, that is, if our shadow price value is greater than zero, that means the our exchange flux will change. That is, the flux will change, and to be the for the metabolic flux, it is essential that our this exchange flux should not change. So fourth will be the answer according to this, because if our exchange flux will increase, so this will we have to reduce our objective function metabolites. We have to remove that.
Okay. Um, Surendra, do you want to share what you understand about shadow price?
As such definition of the shadow price, I'm not getting right now.
Okay.
But positive means we have to increase the objective function. Okay. So and objective function can be increased by increasing the metabolites. So in my opinion, it can be B. Option will be B.
So, okay. Okay, so how to understand shadow prices? Like both of you had mentioned, okay, the definition is it is the derivative of objective function with respect to an exchange flux, and it is given a negative sign. So, how you can understand this is there is a metabolite that is being exchanged. It is either entering your cell or exiting the cell. Now, if I change the amount in if I change the amount in which this uh, Metabolite can either enter, which can enter or exit. Give me a minute, sorry. Yeah, sorry. So how you can understand this is there is one metabolite that is either entering or exiting the cell. It is being exchanged. Now, this is the amount in which this metabolite can enter and exit would contribute to a particular value in the objective function. Now, let us say I'm going to change the amount in which it is either entering or exiting the cell. Then it would now alter the objective function. This is the biological understanding that is needed to understand shadow prices. So, how would it increase or decrease? That is the question that is being asked. So, first, did we understand what biologically shadow prices mean?
Yes, sir.
Okay. So, mathematically, it is given as negative of change of objective function with respect to change of the flux for that particular metabolite. So, this would mean that when we add the metabolite, it would increase Z because more of the metabolite is being available to the cell. This would reduce the shadow price. Whereas if the metabolite is being removed, then the metabolite is not required by the cell. Here, shadow price would be greater than zero. Uh, so the right answer for this question is option D, which is removing the metabolite will increase the objective function value. Uh, was that clear?
Yes, sir.
Okay, okay. Yeah, that is given as the answer here, which is shadow price greater than zero indicates removing metabolite would increase objective function value. Huh. The next question is regions of dual substrate limitation on phase plane are represented by option A alpha equal to 0, option B alpha is greater than 0, option C alpha is lesser than 0, option D none of the above. Before we move on to the right answer for this, if first we'll talk about what phenotypic phase plane is, then we can go to what dual substrate limitation is and then the alpha values. Yeah, anyone can go for it. First, you can define what phenotypic phase plane is. From there, we'll see what dual subset limitation is. Then we'll talk about the alpha values. Is that okay?
Yes, sir. So,
Yeah.
like in previous question, I have
Huh.
said that this objective function, it should remain constant. So for that, in this case, we use two variables, so that if we increase one variable, the another should be decreased to maintain the constant objective function.
So you are trying to say or define what the phenotypic phase plane is with the way you define. Okay. So Surendra, do you want to like share what you think about phenotypic phase plane is?
Actually, no idea.
Okay. Okay. So you one can like adding on to what Kritika said, a phenotypic phase plane can be imagined as a three-dimensional plane, three-dimensional uh, graph, where on one axis you have, let's say, the objective function. The other axis could be one of the variables contributing to the objective function, like flux through that particular reaction. And the third axis could be another variable contributing to the objective function. So what we are trying to get here is when we alter one particular flux, then how does this affect the objective function? And not just the objective function, how does this object change the flux through another reaction? So basically, we are trying to study the relationship between one particular reaction contributing to the objective function and another particular reaction contributing to the objective function. So we are basically studying how flux through the objective function is being determined or being affected by more than one particular parameter. That is what we get from the phenotypic phase plane analysis. Is that slightly clear?
Yes, sir.
Hmm. Now we'll talk about dual substrate limitation. So for a particular cell, like we've seen earlier in week 2, week 3 lectures, there are a few metabolites that are needed as precursor metabolites. Now, and these metabolites also contribute to the objective function. Now, in a particular case where we set constraints, like we ensure that our cell has very limited glucose and another substrate that is needed for its growth. Now, under this condition, it is called as a dual substrate limitation. Both the substrates that are needed for improving the objective function or the biomass, it is limited. This is called the dual substrate limitation. Is that clear?
Yes, sir.
Huh. Now, what they're asking is which of the regions in the phase plane is depicted by dual substrate limitation. So this has a particular value of alpha, which is the coefficient. And with respect to dual substrate limitation, the value of alpha is negative. Uh, if you need the mathematical basis as to why this is negative, we can check lecture 21. I can also attach a video explaining how it is negative. But this is what we need to understand about the phenotypic phase plane and what dual substrate limitation is. What I can do is I can attach a video explaining why it is negative if there is a query regarding that.
Okay, sir.
Okay. Was it fine, Surendra, or do you need some more information on this?
No, clear.
Okay. Hmm. Now the next question is, which of the following technique can be implemented to quantify the relative abundance of 13C carbons in MFA experiment? Option A, HPLC, high performance liquid chromatography. Option B, ultraviolet spectroscopy, UVS. Option C, nuclear magnetic resonance, NMR. Option D, all of the above. We can take a few minutes and then first talk about what an MFA experiment is and how it is being done with 13C carbon. After which, we'll talk about the relevance of the techniques that are being shown here. We'll take a few minutes. Come in 10 minutes. If you're going, just like. Yeah, Surendra, you can start if you want. Yeah,
So, in metabolic flux analysis experiment,
yeah.
uh, flux analysis, na, so we old technique can be used here.
No, no, no. So, what we want here is first we have to understand what MFA experiment is, how it is being done. That will help us understand which of these
Uh,
techniques, three techniques, HPLC or ultraviolet spectroscopy or NMR, is required. So, if you have an understanding of MFA, which is uh, metabolic flux analysis, you can share that with us.
so about the experimentation, I'm not aware, but
Okay. No, a
in,
basic, like, because this was discussed in video 24, lecture 24. So, in case if you're aware, you can share, or I'll go with explaining.
okay, okay.
Ha, yeah. Kritika, do you want to try?
Yes, sir.
Yeah,
Uh, So like here is mentioned there is 13 carbon, which is basically used as a labeling one.
right.
So like if we have a substrate, so that means this 13C will label. For example, I have a 6 carbon substrate.
Okay,
So it's going through a lot of cellular processes.
right.
For example, it's going through glycolysis, then it enters the TCA cycle,
Hmm,
then it's entering the PP pathway, or it can be vice versa.
hmm,
So this will form some bioproducts and biomass and some metabolites as well.
right.
So we want to know, so what's going on inside the cellular processes. So so like it will depend like what number of fragments will be there. Either in those fragments it can happen like not even a single carbon is labeled. In other sets of fragment, there is possibility that single carbon is labeled, and in
Ha,
another sets, two carbon can be labeled, and in last one, all the
all the
carbons which
carbons
are
can
there
be
in the
labeled.
fragment, they can be labeled. And then we have some software which can track these 13 carbon labeled one.
Ha,
So then we can determine the metabolites which are basically labeled with these 13 carbon labeling.
right. Yeah. So, just to rephrase and add on to what you said. So far, what we've learned is about flux balance analysis, where we mathematically try to model how flux has been distributed within a given set of reactions inside a cell. But to validate whether the mathematical methods that we've used is right, what people generally do is they take a substrate like what Kritika had mentioned. Like, for example, let's say there is a glucose. In the glucose, instead of it being a normal 12 carbon glucose, you take a radioactive version, which is an isotope of um, normal 12 carbon glucose. Instead, it's a 13 carbon glucose. Now, what happens is when this glucose is being metabolized, it can be like distributed into different molecules as it enters the glycolysis pathway and other pathways, it gets distributed into various metabolites. But what because of this, what was initially only in the glucose, the 13 carbon, which was initially only in the glucose, is now spread throughout the cell in multiple different metabolites, including all the metabolites that contribute to the biomass. Now, what happens is you take an estimate of how much of glucose is being distributed. Okay, so what you do is you try to determine what fraction of a particular metabolite has this radioactive carbon. So what Kritika was earlier mentioning is called isotopomer. Let us say among the six the ways in when you distribute a radioactive substrate within the cell, a fraction of the newly produced metabolites might have this radioactive label, while the other fraction does not. So these different fractions are called isotopomers. There are softwares that will help in determining this. So what is done is, among the total set of metabolites, what fraction actually has this uh, radioactive label is identified, which is also giving an idea about how much flux is entering the cell. So you know how much glucose you are putting into the cell for consumption as radioactive material. So you know the initial constraint. Now finally you are able to calculate, you're doing a total extraction. Let's say glucose is getting converted and pyruvate is being produced. Let's say you give 1 mole of 13 carbon glucose and you're getting zero point 0.5 mole of pyruvate. Now you know the ratio in which it is being produced, which gives you an idea about the flux that is being carried within a particular reaction. This, in summary, is what is being done in metabolic flux analysis experiments. So, is that clear, Surendra and Kritika?
Yes, sir.
Huh.
What can be the answer here?
So now we've told that the flux, we are trying
Sir, can
to,
I try to explain these options?
yeah, I'll just finish this sentence and then you can try to say why a particular option is not right or it is right. Okay.
Okay, sir.
Okay. So what I was trying to say is, in this experiment, they try to calculate what fraction of the total metabolite is actually radioactive, which gives you an idea about the flux through that reaction, right? So for that, you need an experiment or a measure, a tool that will help you in identifying radioactive uh, elements from non-radioactive ones. So how to approach this answer is, you have to see, or you have to see which of these tools, which is HPLC or UV spec or NMR, is compatible with radioactive substances. That would give us the right answer. Yeah, Kritika, you can. Oh, sorry. Yeah, Surendra, do you have any doubt?
NMR is used. NMR can be used here,
Yeah, NMR can be used. Yeah, do you have? Yeah, NMR can be used. That is true.
but because there's a odd number of protons are there,
Ha.
that's why.
Yeah. Right. The basis of NMR is suitable for estimating radioactive label substances, and you get shifts, chemical shifts, which you can be sufficient.
Mhm.
Yeah, Kritika, do you want to explain why the other two options are not right?
Sir, like this ultraviolet spectroscopy, we basically use to know the absorption, that is the quality for the quality checking thing,
Right.
um,
Why is it
which is
not
not
right?
suitable for this one.
Why is it not right?
Um, I don't know the exact explanation for this.
Okay.
Actually, in
Sorry.
ultraviolet absorption spectroscopy,
Hmm.
absorption happens because of some particular entity of the molecule.
Right.
For example, uh, protein maximum absorption of the protein happens because of the two amino acids, phenylalanine, tryptophan,
Yeah.
aromatic amino acids, na?
Right. Right.
So they are not working at the atom level, like C13.
Huh.
Oh, it is not able to differentiate between C13 and C12 absorption spectroscopy
Right.
because it works for a particular entity.
Right.
Okay.
Yeah, true. What matters in ultraviolet spectroscopy is the total concentration. But what
Mhm.
we need for metabolic flux analysis is what is the fraction of radioactive labels, which so radioactive, just because a particular compound has a radioactive label, that does not mean that it can have a different emission spectra or an absorption spectra. So because of that reason, UV spectroscopy cannot be used to quantify the relative abundance. Like what Surendra had mentioned, it is the entity that matters, and entities do not have altered absorption or emission for just because they become radioactive. And what about HPLC?
So in HPLC, size matters.
Only
Uh,
size?
size of the metabolite
No,
matters.
does it only matter with the size or?
Partition, partition coefficient between the mobile phase and solid phase. Sorry, mobile phase and stationary phase.
Huh, but is the basis of separation size or there's something more to it?
So like it only considered polar molecules, I guess.
Not necessarily. So polar and non-polar molecules can be used with HPLC. Uh, Depending on what solvent you use. Let's say you use a polar molecule, use a polar solvent. Non-polar molecule, use a non-polar solvent, like dissolves like. So both can be used with HPLC.
So
But how,
affinity can be there.
yeah, affinity is the basis for HPLC.
Uh,
So both the mass and the charge plays a role in HPLC.
mhm.
You have a column that has a particularly charged residues, and when you pass a set of metabolites through it, what happens is these metabolites have a particular charge, and they are either bound to the uh, HPLC column or they are eluted, and this elution also have different timings. So this is the basis of HPLC. But just because these metabolites have a radioactive label, that doesn't mean they will have a different elution time. Both the radioactive labeled entity and the non-radioactive entity will have the same elution time because all properties of both the radioactive and the non-radioactive remain the same with respect to the charge and all. So HPLC cannot be used. This is why the right answer for this question is NMR. Was
Mhm.
that clear?
Yes, sir.
Okay. Yeah. Huh. So what they say is in an MFA experiment, a carbon labeled substrate such as glucose or a mixture of uniformly labeled carbon and unlabeled glucose is used as carbon source. The patterns of isotope incorporation into intermediate intermediates are analyzed using GCMS and NMR measurements. Yeah, this is something that we discussed.
So in mass spectroscopy also the separation happens on the basis of mass to charge ratio.
It happens on the basis of mass to charge ratio. True.
So and in gas chromatography it is for the volatile molecules.
It is for volatile molecules. Yeah.
So just adding radioactive carbon
Yeah.
in a molecule is it going to increase the volatility or it is going to change the mass to charge ratio?
So, how you can understand this is like what Kritika had mentioned as isotopomer. Like, for example, in a glucose molecule, you have you can either have only one carbon labeled or all the six carbons labeled. Okay, but you will not give you will not give it just this radioactive labeled substance, but rather you will also give the unlabeled substance also. Now, what happens is because of this, when it is getting incorporated into other metabolites, not all the carbons will be radioactive. Some will be radioactive, some will not be radioactive. There will be some fractions to it. So, you get different masses in a similar range, which will try to correspond to different versions of the same compound. Like, for example, let us take the case of uh, ethanol. Ethanol has C2H6, C2H5OH, sorry. Now, there are three possible variations of ethanol that can be produced when you have uniformly labeled glucose and unlabeled glucose. In the first version, what you will have is zero radioactive label. It is just a normal C2H5OH. The second version, one of the carbon will be having a radioactive label while the other will not. In the third version, the other will be having while the previous one do not. And the fourth version, all the both the carbons will be having this radioactive label. And so because you have this different variations within the same compound, you have an idea about what are all the expected mass ranges. So you get some patterns. This is helpful in determining how this isotope has been distributed. Did that answer your question, Surender?
Yeah, got it, got it.
Okay. Huh. Now calculation of basic vector. So they have given us a reaction network and we have to calculate the basic vector. So what you can do is you can take a few minutes and try to solve this problem. If you're unable to do so, I'll explain how this has to be done. You can take a few minutes. Yeah, we're able to calculate the basis vectors, or should we start with what basis vectors are? Hello, can you hear me?
Yes, sir.
Yeah. So, uh, were you able to calculate the basis vectors for this reaction, or can we
सर
discuss?
ये कंसेप्ट मुझे क्लियर हुआ ही नहीं, 3
Oh,
बार लेक्चर देखा था उसके बाद भी।
okay, okay. Surendra?
Actually, not able to answer.
Okay, okay. So, you know what this network is. You, from this network, now we are capable of writing the stoichiometric matrix, correct?
यस सर।
Okay, so first what we have to do is first we have to write the stoichiometric matrix, and then we know the steady state condition to calculate the null space, that is S dot V is equal to 0. Okay, that will give us something called as the flux balances. So this is the stoichiometric matrix. This is the flux vector. When we put that is equal to 0, what we get is V1 minus V2 minus V5 equal to 0. Similarly, we'll have now basis vectors means you are trying to redefine this entire network in the combination of two vectors instead of having. So now we have five different unknowns. We have to quantify five different values to be able to describe how this stoichiometric matrix works. Instead, what we can do is we can use two different vectors and try to come up with an equivalent for how the stoichiometric matrix works. Okay, so what we do is we will see which of these two different which of these how do I say fluxes can be used for representation purpose. So first we can rewrite these equations. When we rewrite these equations, what we guess is V2 is equal to V3 and V3 is equal to V4 minus V5. Whereas here we can write V1 is equal to V2 plus V5. How it has been described in the previous case in the lecture is that you take two different, they define that fluxes in terms of two different fluxes, V4 and V6. But for our case, what we can do is we can take, for example, here V3 is represented twice and V5 is represented twice. So we can take V3 and V5. So first step is to rewrite this V1, V2, V3, V4 and V5 in terms of V3 and V5. Okay. So if you do that, V1 will be equal to V2 minus V5, V5. But V2 is already V3. So how we will write V1 is V3 plus V5. Is that clear?
Sir, can you again repeat these?
Yeah. So what we are trying to do is, see, we have three different equations, five different unknowns. It is not possible for us to solve this equation easily. Instead, what we are trying to do is we are trying to represent this vector in terms of just two different vector. Sorry, this set of fluxes in terms of just two different fluxes, relative values. Okay. So what we can do is we can choose two different fluxes. For our case, what I'm taking is V3 and V5 because these are there in more than one equation. That way, if you rewrite, V2 is equal to V3. Okay.
Yes, sir.
V1 is equal to V2 plus V5. But because we know V2 is equal to V3, we can substitute that in V1. So V1 is equal to V3 plus V5. Okay.
Yes, sir.
So if you write in terms like that, you will get here V1 is equal to V3 plus V5, correct? V2 is equal to V3. V3 is equal to V3. V4 is equal to V3 plus V5. And V5 is equal to V5. Is that clear?
Just a second, sir.
Yeah, you can make a note of it. V1 is equal to, I can even type here. I'll type here, you can make a note. V1 is equal to V2 plus V5. V2 is equal to V3. V4 is equal to V3 plus V5. Now, because V2 is equal to V3, you can rewrite this equation as V1 is equal to V3 plus V5. So if you do that, this particular matrix, it can be represented as V2, sorry, V3 plus V5, V3, V3, V3 plus V5, and then V5. Is this clear?
Yes, sir.
Okay. Now you got this. Now you have to decompose this matrix into a combination of two vectors. How can we do that? We know we have V3 and V5 here, correct? So what we'll be doing is we'll split this such that now we take V3 out. If we take V3 out, in the first equation we'll have 1. Similarly, if we take V5 out, again in the first equation we'll be having 1. This is equivalent to this. Okay, is it okay?
Yes, sir.
In the second equation, only V3 is there. V5 is 0. Same with the third equation. Whereas fourth equation is same as first equation. And the fifth equation is V3 has a coefficient of 0, whereas V5 has a coefficient of 1. So we can rewrite this set of equation like this. Okay.
Yes, sir.
Okay. Now the basis vector here is this set of coefficient, this 1 1 1 1 0 and 1 0 0 1 1. These two are called as the basis vectors. Is it clear?
Yes, sir.
Mhm.
Now,
Yeah, yeah.
now what we have to do is, this is all arbitrary. See, I had 5 different variables, V1 to V5. I myself chose V3 and V5. I can rewrite this equation based on convenience with what I can do. So first what we have to do is, once we get these basis vectors, we have to redraw the metabolic network according to what we have. So how do we do this? They are saying V3 is positive across uh, V1. Okay, okay. Just to give a clarity, this is V1. This is V2. This is V3. Sorry. This is V4. This is V5. And that same thing applies to this also. So now we have to see if whatever basis vectors that we have got here also stays true with respect to the metabolic network that has been shown here. So wait, let me bring this data there and then we'll see. This is nothing but V1, right? And so and so. Right. So now if we have to draw and see if this is right, how we do is V1 is equal to V3 plus V5. So this can be written as 1, 1, 1, 0, 0, V3 plus 1, 0, 0, 1 and 1. So when we are drawing this can be known as basis vector B1 and this as basis vector B2. Now B1 they are saying it is all positive. In B2 it is also all positive. But it does one of the basis vectors here matches the basis vector here, but the other one doesn't. I'm not sure if the fluxes that they are taken is V3 and V5. So although we got these basis vectors, I am unsure if these are the right basis vectors because they do not correspond to the answer that is being shown here. So what I'll do is I'll check and I'll append as a video here so that you can check it on YouTube. But this is the method to calculate the basis vectors. I
Okay.
will I will just check why a particular vector is not right, and I'll update it on YouTube. Okay,
Okay.
Okay, sir.
thank you.